So for this part, I want to discuss mean value theorem for integrals. Okay? I hope you remember the mean value theorem, the one that you had during your calculus 1. So in here, we will consider the mean value theorem for integrals. So what is this guy here? What is this theorem? Recall that if you have numbers y1, y2 until yn, you can get the average of this. Okay? The average, you just have to add these numbers and then divided by the number of numbers you have. So n divided by n. Okay? But what if you have infinitely many numbers? Okay? In fact, what if you consider all the numbers on an interval? How do we get the average of that? And what if you have a function defined on that interval? Can we get the average of the function over that interval? Of course, if you have an interval, it will have infinitely many points. So if you evaluate it to the function, there's infinitely many values. So how do we get the average? Is it possible to get the average? The answer is yes. The answer is yes. So how do we do that? So let f be defined on an interval AB. Find the average value of y equals f of x over the interval AB. Okay? So to do this, it's similar to how we derived definite integrals. And therefore, in here, what we are actually going to do is an application of definite integral. So average values is an application of definite integrals. So let's see. First, you divide the interval AB into n subintervals of equal length. So let's make it equal length. So that you have your delta x equals b minus a over n. Choose sample points, x1 star, x2 star until xn star, 1 for each subinterval. Compute the average of the numbers. You have n subintervals, you have n sample points. The average is simply f of x1 star plus f of x2 star plus until f of xn star divided by n. That's the average. That's the usual. And this is possible because there are only n values. Okay? And then what we're going to do is the following. Since delta x, this is equal to b minus a over n, or your n can be written as b minus a over x. So you cross multiply this. Your n in the denominator earlier, so here, we will replace it by b minus a over delta x. Or this one can be now written as f of x1 delta x plus f of x2 delta x plus until f of xn delta x. Where the xi's, we have the star there. Okay? And then divided by b minus a. But look at the numerator. It's just a Riemann sum. Okay? And then the over b minus a, you can just bring it out of the sum. You have 1 over b minus a times this Riemann sum. Therefore, if we let n approach infinity, okay, we will have the following definite integral. So letting n approach infinity, the limit as n approaches infinity of 1 over b minus a, sum of x I star delta x I from 1 up to n this guy here, if it exists, okay, if this exists, this is just the definite integral of f of x dx from a to b. But don't forget this 1 over b minus a. But what does this mean? When you let n approach infinity, you are making the subintervals as small as possible, that as if the only sample point you can get is the point on the interval, which consists of a single point. Okay? So what I'm saying is, if your n is very, 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 very large, okay, it would seem that there's only one point on that interval. Of course, there's infinitely many sample points possible. Okay? But letting n approach infinity would mean that there will be possibly a single point on that interval. And therefore, you are actually adding all the values of f of x, okay? And then if you divide it by b minus a, what you get, okay, is the average value of the function. Okay? So we define the average value of f on the interval ab as, so we write it as f av. This is 1 over b minus a times the integral from a to b of f of x dx, provided f is integrable on ab. Okay? Example. Suppose you have a function f of x equals 1 plus x squared on the interval negative 1, comma 2. You want to get the average. So f av, not fav, but f av, this is 1 over 2 minus negative 1, and then you integrate from negative 1 up to 2 of 1 plus x squared dx. So here we have 1/3. 1/3. In here, if we evaluate this, we'll get x plus x over 3, x cubed over 3, evaluated from negative 1 up to 2. So this is equal to 1/3. 1/3 times. At 2, you have 2 plus 2 cubed over 3, minus. At negative 1, you have negative 1 plus negative 1 cubed over 3. So if we simplify this, we have 1/3 times 2 plus 8/3 minus minus. So minus minus, that becomes plus 1. In here, negative 1/3, negative 1 raised to power 3, that's still negative 1. So this is still minus, but we have minus there. So we have here plus 1/3. So if we combine, we have here 2 plus 1, that's 3. 8/3 plus 1/3, that's 9/3. So you have 3 plus 3, correct? That's 6 over 3. This is equal to 2. So the average value is equal to 2. So meaning, what does this mean? If you have this, and you have the squared function from here up to here, so say at this point up to this point here, if you collect all these numbers in between or on the graph, which is infinitely many of them, okay, So if you collect all of these values here, you add them, you divide by the number of objects that you have, that's equal to the 1 over b minus a, you will get 2. That's what it means to have this average value. Okay? Questions? Now, what is this mean value theorem for integrals? If f is continuous on the interval AB, so take note, this is only the condition. If f is continuous on the interval AB, then there exists a number c inside the closed interval AB such that f of c, that's equal to the average value. Okay? And what is this average value? Again, from the previous definition, it's just 1 over b minus a integral from a to b of f of x dx. Or if we manipulate this equation here, it means that the integral of f of x dx from a to b, so this guy here, it's equal to the average, okay? It's the average of the function times b minus a. Okay? So for example, this blue curve here, this is your function. You consider the interval AB. Okay? The theorem says you will find a C between A and B such that if you evaluate that, you will have your f of C. And this f of C is your average value. Okay? And furthermore, if your function is non-negative, okay? If your function is non-negative, you consider the area under the curve. You consider the area under the curve. That area under the curve can be represented by an area of some rectangle. So this is your rectangle here. There's an area on that. That's the same as the area of the region under the curve. Okay? So that's mean value theorem. So remember, the only condition for mean value theorem, it's just continuity on the closed interval AB. Okay? Example, let f of x be equal to 1 plus x squared for negative 1 less than or equal to x less than or equal to 2. Verify the hypothesis of MBTI for this function. Then find a value C that satisfies the conclusion of the theorem. Take note, so since f is a polynomial, remember, any polynomial function, it's continuous everywhere. So for our function f, since f is a polynomial, f is continuous on any given interval. In particular, we have the interval negative 1, 2. That's the only condition. So MVTI, so mean value theorem for integrals, applies. What does this mean? Therefore, or thus, there exists a function, there exists a number C. There exists a number C in between or inside the interval -1, 2, such that the integral from -1 up to 2 of f of x dx, this is equal to f of c. So f of c times, what is this? So f of c times 2 minus -1. But 2 minus -1, that's 3. So you have here 3 times f of c. But what is this integral in here? Okay. Or in here, or your f of c, this is 1/3 integral from -1 up to 2 f of x dx. This guy we have calculated. It's this guy here, correct? We found that it's equal to 2. We found that it's equal to 2. So in here, this is just equal to 2. But the question is, what is the value of c? Look, this is just f of c. You have 1, 1 plus x squared. That's your f of x. So f of c, it's just 1 plus c squared. Okay? Now, f of c, this is just 1 plus c squared. So you have 1 plus c squared. This is equal to 2, which therefore gives us c squared equals 1. So that's 2 minus 1. And therefore, c is equal to plus and minus 1. Okay? And take note, you have two values. You have to check if they are inside this. It is possible that there's only one inside. Okay? If there's only one inside, then that's the only one you get. Inside and also including the endpoints. But in this case here, both -1 and +1 are inside, are in the interval -1, 2. Okay? So so both c equals 1 and -1 satisfy the conclusion of MBTI. Of MBTI. Okay? Questions? Okay? Then one last problem for today's session. Find the average velocity of a car over time interval t1, t2. So what's the average velocity? So if s of t is the position function of the car, and v of t, this is equal to s prime of t. So this guy here is the velocity function of the car, then the average velocity, then the average velocity is, so you have VAV, I'll just write this as VAV, but this is just 1 over T2 minus T1, okay? Integral from T1 up to T2 of V of T dt, okay? But V of T, it's S prime of T. So you have your 1 over T2 minus T1, integral from T1 up to T2, sorry, that should be T2 there. So this guy here, it's now S prime of T. And you know what will happen to this? In fact, from here you can easily get that one. It's 1 over T2 minus T1. And this guy here, remember that this is just the displacement. S of T2 minus S of T1. Or simply, the change in position, S of T2 minus S of T1. So the change in position over the time elapsed. So this is the average velocity of the car.